Well, welcome everybody to Session G, Case Studies in Post-Harvest Loss Intervention, or Prevention, sorry. I'm John Bowman from USAID. I'll be chairing the session. We'll start off with a keynote presentation from Dr. Dirk Maier, and then that'll be followed by 5 subsequent presentations on the area of post-harvest loss prevention. So right off the bat, I'd like to introduce Dirk, who will be giving the keynote for this session. I first got to know Dirk at Kansas State University. He was the heart and soul behind the Kansas State University Innovation Lab, and the co-director, lead PI. He launched the project, but subsequently has moved to a new position at Iowa State as the Associate Director of the Global Food Security Consortium. But his research is still very much aligned and focused on post-harvest issues and interventions in the area of food security. So without further ado, I'd like to have him come to the podium and present his talk on post-harvest loss intervention strategies.
Thank you, John. Get this started here. Thanks so much for the introduction and the opportunity to be here. I know that not everybody is in the room from the whole conference, and I don't know whether Prasanta is in here, but I just do want to give a shout out to Prasanta Kalita, Dr. Kalita, who's been doing just a fantastic job getting all of us together and organizing the conference. I know he's thanked a lot of people, but many of us have not had a chance to thank him publicly, and so I do want to take this opportunity to acknowledge his leadership and the pleasure and joy I've had working with him and his entire team over the last year and a half, and of course many others. So I was asked to give an overview about some intervention strategies and show some examples of some case studies. But before I do, I just want to tell you just a moment about the Global Food Security Consortium that is at Iowa State University. It is kind of a worldwide initiative that was established well before I came there, partnership with multiple universities, research institute, and really if you have an interest in that, there is a website or you can give me your business card and we can send you information and connect you to that. What's intrigued me about this particular consortium is just the fact that it works across multiple platforms, really from the seed and science, seed systems, germplasm side, all the way through production, utilization, and policies and regulatory things. So we're very open to many different scientists, researchers, faculty, students, and others that are interested in collaborating on that together for the purpose of food security. Now, one of the things I thought about leaving this slide out, but even over the last couple days, I don't think we've really put out what the definition is of food security. We keep talking about it. And from our consortium's perspective, global food security is essentially consistent with the definition of food security as FAO has defined. And I really like that because food security is really achieved based on this definition when all people at all times have physical and economic access to sufficient, safe, and nutritious food to meet their dietary needs and food preferences for an active and healthy lifestyle. There's a lot of aspects in there. We're not going to dissect that, but I think if we can keep that in front of us, I think that also creates the goal of everything that we're trying to do in terms of reducing and preventing post-harvest loss as well as food waste. So I want to just share that and keep that in front of us throughout our time together at this conference as well. So, intervention strategies. And I'm an engineer, so I primarily put together kind of the intervention strategies that are generally out there from an engineering technical type of perspective. And they, from our perspective, fall into 3 main categories related to drying the grains and cereals. And again, this is focused on grains, not on fruits and vegetables or roots and tubers, although some aspects, of course, apply in terms of technology. Storing grain with different technologies, monitoring grain with different approaches and so forth. And I want to just give a little bit of an overview. There's been a lot of papers yesterday, today, as well as tomorrow, and posters that have dealt a lot more in depth into every one of those technologies. I'm looking at it a little bit more from an overview perspective rather than diving into each of them in detail, but I will give a few case examples to kind of further illustrate that we need to approach things from a holistic and systems perspective, and that oftentimes while we can know or already know and could implement the technical solution, it isn't necessarily the issue that prevents us from making advances with regard to the reduction of post-harvest loss, as we've heard, again, in numerous presentations and conversations here at this conference. So, solar dryers, mechanical dryers, sun drying with so-called natural or forced convection air, mechanical dryers with fans and burners, the hermetic storage technology, mostly bag storage, but also metal and plastic systems, the protection technologies that are out there in terms of grain protectants, various types of products that are available, and then the monitoring of the grains. Again, moisture content is a key aspect. How can we measure aflatoxin, mycotoxin easily? How could we monitor some of these modified atmospheres, which are basically changes in gas concentrations in the storage structures, and how do we monitor insects and whatnot? Pictures, we've seen these. When I first was at Michigan State University, a graduate student, I had the great honor to travel with my major professor to China, Northeast China, in 1987, which was really before most people were allowed to travel, or even Chinese were allowed to travel out of the country. And this is the kinds of things that we saw there in terms of corn or rice, oftentimes being laid along the street. But this is still the same picture that one of my colleagues took just here recently, the last 3 years, traveling in Africa and whatnot. So the problem and the challenge has been with us throughout the decades. And again, we know what the solutions are technically, but there are reasons for why certain drying technologies have not necessarily been adopted. Here's some current drying practice in Guatemala. My colleague, Dr. Carlos Campoadal from K-State, has been very much involved in this project with the Post-Harvest Loss Innovation Lab, and just illustrating again here that in Guatemala and the Western Highlands in particular, corn is typically harvested on the ear and then dried on the ear or kept on the ear in the attics and whatnot. And so for us to come in and say, hey, let's just shell this, let's just dry this on the kernels and so forth, it doesn't necessarily work because the cultural setting is different. Most of the grain that they're producing, or most of the corn that they're producing there, is used for internal food consumption. And so we need to be sensitive to that understanding of that cultural practice. Again, when you look at 85, 90-some% of drying is going on of what they're harvesting there, and a lot of it is dried by sun or just exposing it to the environment, no forced drying. And so that's why when you're looking at what they're handling in terms of maize storage, what they're harvesting is basically stored on cobs in the attics or on the rafters. And so what's going to happen is that's what they're storing it. So the maize that they're producing is stored in the attics. And so you ask yourself, well, where does kernel storage come, the bulk storage? In bags versus silos. Well, that actually comes from the corn that they're buying, because they're only self-supplying about a third of the corn that they're consuming. And so, again, that changes totally the dynamics of how you might come in with a suggested intervention strategy in this type of a system where the farmers are actually consuming a lot more corn that they're buying in the marketplace and have no control over how dry, how much mycotoxin and other types of characteristics might be in there. But then when they bring it home, why they might want to store it in a bag or how we might get it into a silo. Again, a unique aspect in this particular region. Drying systems. GrainPro has developed that solar bubble dryer. That's one system that's available. Erie was involved with that, University of Hohenheim from Germany, which has worked in the solar drying area for more than 30 years and have gone through various designs, very applicable also for other products, vegetables, fruits, woods have been dried with these types of solar dryers. Also, the solar dryer, this S4S, is an Indian engineering firm / university that's developed a higher capacity type of solar drying system. Either they are used with convection that is forced through an airflow, or they're basically natural chimney type. This is a setup of one of our projects from our colleagues in Bangladesh that are actively testing the system with maize and rice paddy in Bangladesh at Bangladesh Agricultural University. I appreciate them letting me use their pictures. You've seen some of the posters where they have had details of the research results from this particular trial. And this is work that's been done in the AfloStop project, again, evaluating solar type of dryers. And when you look particularly at those types of two systems, One of them is natural convection as a result of these types of chimney effects, the same design as what Beth showed this morning, or you put some kind of a blower on the front of it to kind of increase the airflow over the surface to enhance the type of drying that you're trying to achieve. And so my main point from an engineering perspective is, okay, this is wonderful. We were able to reduce moisture content in this layer, in this forced convection solar drying system from 17.4% down to about 15.6%. But how long did it take? Oh, 7.5 hours. That's quite a lengthy time compared to if I'm in a business of providing dryer services where I might want to dry something in 3 to 4 hours versus taking an entire day for one batch to be dried. And lo and behold, actually, I'm not even getting down to the general recommended storage moisture content of 13 to 14% in a 7.5 hour time period. In other words, I would have to extend this drying further, maybe have to hold it through the night and then continue the next day. So these are some of the pros and cons when you start looking at that. So there's a number of solar dryer systems. These, again, were pictures from colleagues, Dr. Sam McNeil and Dr. Klein-Leligy. They've taken pictures in Ghana, in Nigeria, where there are solar dryers that have been out there. Many of them are not being utilized. A lot of them have poor drying efficiencies. Their design, fabrication, and maintenance challenges, and durability of the dryers in the absence of local expertise often make them be abandoned after a relatively short period of time as part of the challenges. Here is another project out of the AFLOSTOP design, and Sophie Walker was kind enough to let me use the data that she has generated in her team. Primarily here you're looking at a shallow bed type of drying system. In other words, we have some type of a plenum structure to hold it up, perforated type of drying bed where you can put various crops on there. They're focusing primarily on maize. In Kenya, we have an interest to look at this dryer for the use of ear corn drying in Guatemala. And the key design part is how to build a burner-fan combination where you could use corn cobs, wood, and other types of biorenewable materials for operating this type of a system. But the advantage is you have a forced convection airflow through the system. And these, again, are various systems here on a relatively smaller dryer, a little larger drying bed to get up to about 500 kilos or so forth, the tarps to keep rain off. So a lot of good thinking has gone into those systems, and they've really generated a lot of excellent data to be commended in that regard. And so when you look at the research results that they have generated, again, I'm looking at how much moisture content are we removing, and in these types of tests, we're somewhere between 3 to 5 percentage points, which is very good, and we're starting to have 3 to 5 hours type of time frames, which I think is important. And we're even in one system getting to about 2 percentage points of a drying rate. And so when you start thinking about providing a drying service business, and you go to a farmer or a group of farms or community where they're bringing batches of grain to you, you have to be able to turn the batches over in that dryer within 3 to 4 hour periods. If you have a drying system that's going to take multiple days to dry a batch of grain, you cannot provide a service business unless you have many, many different dryer systems available. And so this kind of comes back to this cost-benefit ratio of saying, hey, if we're going to design drying systems, let's also think about the engineering parameters, the time it takes to achieve a drying process. And so again, when you're talking about 2 points per moisture, you're starting to make some significant progress in the right direction. Our friends in Bangladesh have tested this so-called STR drying system with essentially, using bamboo mats on the inside and on the outside to create essentially a conical drying system, which again is a drying system that's been around for a long time. The bamboo mats allow the air to penetrate. They've got a burner system and a direct-fired stove that they're feeding, which works for paddy rice because you're removing the husk. You can't do a direct-fired burner with maize because, again, if you're using that for human food consumption, the flavor on that and the carcinogens are not going to be something that will be desirable. And so then when you're looking at this type of a drying system, again, it shows the concentric circles here. We're beginning to see, hey, we're getting from 18% moisture content down to about 12% moisture content, and we can do that in about a 3-hour time period. And that means, too, that we're achieving drying rates of about 2 percentage points per hour, which, again, is in the right direction with regard to where you need to be. We've also traveled and looked at what are local solutions? How can you build those systems with as little engineering, manufacturing technology as possible, or how can you utilize materials locally? Carlos Campadona, we had a chance to travel in Laos last fall, and there we visited a fellow who basically said, hey, we can build metal silos using the sheet metal material that's readily available in our country. We got to just have somebody that bends those into curves so we can build a bin. And that's what they did. All of this is local material that usually would be used for sidewalls for metal shacks or roofs on buildings. And then they put floors in there with beams, wooden beams, with support structures, so you create a drying floor. They would use wood-burning furnaces that they enclose in bricks or concrete blocks, and then they blow air or suck air across this for heat exchange to get enough of a temperature rise to get a very nice drying process going. Maybe not the most efficient, but definitely functional and effective. And the only piece that is not from Laos is Chinese blowers, because there's nobody locally that manufactures fans. And so they were utilizing blowers from out of the country, which is fine. They're relatively inexpensive. Here's an example of a similar system that they built, and this one is for fruit drying. So in this case, they had the same setup, but they're recirculating the air back out of the drying system and through, because they're putting on these beds, either suspended or fixed, mango slices. Yesterday, somebody was talking about mangoes and preserving those, and they're reducing moisture content just about to maybe 30-some%, putting them sort of vacuum-packed plastics, and they just extended the shelf life of the mangoes to several extra weeks, and they can take that to the local market. But again, not a very efficient process, but it definitely is functional, and all operated with corn cobs that had previously been shelled, because they're also growing corn in that area, and can use the same dryer for corn on the ear or shelled. So again, very functional, excellent case studies and examples. And guess what? Those of us from developing countries, lest we forget, just 50 years ago, this is a USDA Ag Research Service publication, 919, you can Google it, you can get the e-copy. In 1963, we're still giving advice to farmers in the Midwestern US how you can convert a standard silo that had only been used for dry grain storage and make what? A drying bin out of that, a silo. How do you do it? Well, you take wooden, concrete blocks, you take wood 2x4s, you take hardware cloth. Same idea as the fellow in Laos. You take some portable type of system with a blower and a burner, either electric or a gasoline engine to drive the fan, or oil, diesel oil, fuel oil, or gas burner, all of that, which is 50 years ago. So these technologies have been around for a long time that we can make work. All right, how about on-farm storage? Here's an example of a storage system underground in Ethiopia. Our colleagues that have been involved with the Ethiopia project have taken, but a lot of insect and mold damage on these particular things. And if you look at insects and the tremendous damage that they do, this is just illustrative. When you have a jar of wheat, okay, at day one you put 100 adults in there for 7 days, and then you remove them, leave this sit for 128 days, you have nothing but consumed residual material left. That's how damaging insects are. And of course, we've heard a lot about hermetic storage bags, whether those are the PICS types, whether that's the GrainPro types where you have an oxygen limiting barrier in the plastic. You can configure those when you have the plastic layers. There's only so many companies in the world that make these large sheets and extrude them in 5 layers with an oxygen barrier. Those are commercially available. It's a matter of buying the rolls and making the bags of any size. I mean, there is obviously a tremendous skill set involved with that, but the sourcing of the plastic liner is actually not very difficult. We bought a roll like that a number of years ago, and we made our own bags out of that by welding, sealing, heat sealing the bags together of various sizes, so that is possible to make. Metal silos, a lot of different designs. There's a wonderful example here from the World Food Program on display. Again, metal silos have been around for a long time, and they come with various designs. So again, if we go back to our case study in Guatemala, we know that the farmer is basically drying here on the ear, has to more or less hand shell, but they hand shell because on the day that they want to make masa, they hand shell so many cobs, and so it's not a big deal. So that's why it's not very convenient for them or to us to expect that they're going to end up putting this corn in these bags or in these metal silos, because they're only shelling by hand what they're going to consume. So this bulk storage only applies for the maize that they're going to buy that doesn't meet their demand, which they have already used up third into the season. Or you have to have some kind of a shelling technology to shell the ears to then put the maize in a bulk handling and storage type of a system. Another technology that we've worked on and the Australians have worked on, this is a little larger size, but again, we're talking metal silos and the sealability of the silos. And what does that mean? How tight does a metal silo have to build in order to be considered sealed? There's a lot of work that's actually been done in the fumigation, gas fumigation area. And this is an Australian silo that we just set up at Kansas State with a so-called thermosiphon system. Then we took one from a U.S. manufacturer that donated to us and knew what we were going to do with it, so we give them a lot of credit for that. And we sealed it with caulking material to see whether we could achieve the same air tightness or gas tightness as we did in the Australian silo, and we can do that with pressure testing, which works very effectively, and we got very close. And then this natural convection thermosiphon is a recirculation system that actually makes sure that the fumigation is effective. And again, in some larger bulk systems where you start bringing things together in an even developing country setting, it's very important. So when we're looking at the gas concentration in the sealed silo with thermosiphon and the gas concentration in the sealed silo without the thermosiphon, which allows the gas to distribute more quickly, we're learning that in this case with the thermosiphon, we're able to achieve the concentration time product quite high. In this one, we were not able to achieve it within a normal 72 hours, and the phosphine label requires this, and this kind of goes towards why phosphine is creating resistance problems among insects, which is another reason we have to think about intervention strategies in the storage site. So being able to seal a metal silo properly, keeping that seal, and having it airtight, so when phosphine fumigation, which is given tablets to farmers who have a metal silo in their living room because they want to protect the grain that is leaky and is exposing the family in their bedroom and living room overnight, is an absolutely dangerous and irresponsible way, in my view, to start storing grain in bulk in some of these developing country type of settings. So we need to think about the gas tightness of these metal silos if we're going to try to advise people with regard to fumigation as well. So that's very important. Now, the third category, improving monitoring of grain. This here, we'll look at moisture and aflatoxin. This is some work that's being done by colleagues at the Food Process Innovation Lab at Purdue University, looking at how can we build devices that easily measure temperature, humidity, and moisture content. And it's excellent in terms of what they're trying to achieve in that regard. There's also work that's been done by Dr. Paul Armstrong from USDA in Manhattan, and he has developed probably what I would consider at this point in time the best road towards having a reasonable moisture sense. I think Sam McNeil, who is here, was at a poster session, has a unit with him, so if anybody's interested, go ask Sam to see it, demonstrate it. But here all of a sudden, we can use with a sensor that measures temperature relative humidity, we can put it in a bucket of grain, we can probe it into a drying bed, we can probe it into a cocoon, we can probe it into a sack, and very readily determine the moisture content. If you don't know what the initial moisture content is that you're trying to dry, or the end goal of drying, or know whether your grain is safe for storage before you put it in a bag storage or anywhere else, you have no way to really manage your inventory. So having something that lets us measure moisture readily and relatively inexpensively is absolutely critical to make progress in reducing post-harvest loss and moving forward with drying and storage systems. Here is an example. Moisture meter was donated to our project through John Deere. Wonderful moisture meter, but it's a lot more expensive, and so it would only be applicable to maybe an aggregator or somebody that has a lot more grain. And this farmer here, he was shelling his corn, and we're basically testing him. What do you think the moisture content was of your grain versus then the moisture meter? It was just astounding, the difference. Even though he dropped it on the floor, he bit it with his tongue, he tried to make salt stick to it, he was always 2 or 3 percentage points off than what the actual moisture content is. And so again, moisture measurement technology that's reliable is absolutely important for bringing drying services and storage systems to people. Mycotoxins, another very important thing. Again, in Guatemala, where people eat a lot of corn tortillas, if you have aflatoxin presence and constantly eat corn tortillas, you're going to have an overexposure to aflatoxin. There was some wonderful work that's been done by a nutrition science person in Dr. Torres in Guatemala, has for several years already, collaborating with USDA and collecting data on mycotoxin in the country. And what we're finding, this is a complicated chart, we don't have enough time to discuss it, but the bottom line is that the green areas or regions in Guatemala are the regions that are underproducing corn for their self-consumption, and the yellow areas, I'm sorry, the other way, the yellow areas don't produce enough, and the green areas overproduce. And so actually what we're finding is that in the highlands of western highlands of Guatemala, the aflatoxin problem of self-produced corn is actually not as high as people thought. And the problem is actually coming from the corn that is grown in the lowlands where temperatures are higher, humidities are higher, mold and mycotoxin are a bigger problem, but that corn finds itself in the marketplace in this region, and people are buying 2/3 of the annual supply from these regions who have high contents of aflatoxin. So if we try to solve the aflatoxin problem here in terms of consumption, we actually have to solve the aflatoxin problem here where the majority of the grain is produced. Again, understanding the cultural setting and the country setting is very important as we try to bring intervention solutions to that. Modified atmosphere, hermetic atmosphere. All hermetic really means is a reduction or elimination of gas exchange. And you modify the atmosphere by changing the gas concentration from an oxygen-rich environment to an oxygen-low environment, and ideally low enough so that insects and other pests would basically suffocate and no longer reproduce and cause damage. My good colleague and friend, Dr. Ricardo Bartosik, has done just tremendous work bringing CO2 measuring technology from lab research when we did that way back at Purdue to commercialization of these large silo bags in Argentina and Latin America. Again, Ricardo can tell you more about that. So it is possible to measure the oxygen and CO2 environments in these modified hermetic storage systems to know how effective they are or not. And this is some great work my colleague Dr. Carl Byrne and his team have done here recently at Iowa State University to actually just quantify how much oxygen do weevils, for example, consume? And if we know how much oxygen they consume, could we actually predict how long it would take in a storage structure that's a bag before a modified atmosphere below maybe 4% oxygen is established, and then how many days you would need to keep the bag sealed to assure that all the insects are dead? Wouldn't that be a good idea? I think it's a good idea, and engineers have been able to calculate that. So it allows for the prediction of time to mortality at 40% oxygen in any hermetic storage system. And so in this case, an example, he predicts that a 100 kg PICS bag could, within 9 days, reduce oxygen below 4%, and then on the 10th day and beyond, it would basically be insect-free. At that point in time, you could open the bag theoretically, take grain out, reseal it. If no insects got back into it, that bag would be perfectly fine, and you really don't have to reestablish a 4% oxygen environment for that hermetic bag to continue to be effective. It's just a fact of physics and biology. So I think very knowledgeable. So anyhow, as we kind of summarize here, and as I come to the end of my talk, the point I wanted to make is that, again, the technology exists. I think we as engineers can do a little better job to help our other colleagues understand how the technologies work and the engineering physics behind it as to why they work and why certain parameters are required, like amount of airflow and heat rise to achieve a certain drying rate, or reducing the oxygen concentration in a hermetic storage environment in order to achieve the mortality of insects and how to measure that. And then we can look at what combination of these systems might be applicable considering all of the other parameters that are important in order to potentially bring an intervention technology to bear, which, again, the technology solution might be the easiest part, and the other cultural, economic, and other types of parameters, social parameters, are actually the barriers that allow us to move forward in that regard. So thank you for the opportunity to share that overview, and if any questions later, be more than happy to answer that. Thank you.
We have time for a few questions now because we started the session about 12 minutes late, and Dirk stuck to his time in a timely fashion, so he's if there's any questions at this point, please raise your hand and Dirk will try to answer. Would you have a microphone, please, down front?
Thank you very much for the interesting presentation. Suntory, Chamley Press. I just wanted to find out a bit more about how much you use local knowledge from the people that you work with in terms of local technologies, yeah, local knowledge. Is that something that when you go to design these things that you consider?
Yeah. If I understood you correct, you're asking how much also local knowledge is used. So again, I would go back to the example where we're in Guatemala. We obviously came in there with a certain preconceived notion based on what we thought we knew from literature and so forth. And until our team got active, learned the setting, the situation, how maize is produced, how it's harvested, how it's being stored, drying and so forth, we started to adjust as quickly as we could to that. So for example, we used a drying system that had never been used in this part of the Western Highlands. We ran into some issues, quite frankly, and we all understand what the causes of the problems were, that the fan, the burner, and things weren't functioning quite as well as we had tried to design. And so we went back to the drawing board, but we also went with the students that were involved. They were all local students from university in Guatemala City. Said, hey, let's go to the local hardware store, the local steel, people that can manufacture steel, and talk with them as to how could we take this design and simplify it and use local corrugated sheet metal, wood structures, and other ways that the next generation of the dryer, which we're currently in the process of testing, could then perhaps be less expensive and more affordable and so forth. The second part of that example is we lugged up their car batteries because we thought we needed to run the fans off electric power, off the grid. Well, each car battery cost about $100 US bought in Guatemala City at an auto supply store. Well, it turned out the farmer had electricity, 25 to 30 amp service, and he was more than willing to have it used for the purpose of drying, and that eliminated a huge cost on that particular system. And then we learned later on that close to 75% of farmers in the Western Highlands in Guatemala have 25 to 30 amp services where you could actually run a fan if we can do it within 4 hours at a very inexpensive electric cost and not have any burden on the system. So that's how we try to approach it, and I hope that answers your question. So.
Any more questions?
Hello.
Okay.
Thank you, Dr. Maier. I was happy to see the raised metal storage bin as an option. Could you elaborate on how hard it would be to line that bin with the plastic bag material and seal it hermetically?
We were able, in our view, the metal silos that we were working with, particularly if they're designed to begin to go together in such a way that it is sealable, like we were able to, that we would not necessarily see a lot of benefit of putting another liner in there to create a hermetic storage situation. However, it could be if that's how you want to use the structure, but at the same time I've seen examples of using a plastic bag system that you can set up as a silo, and it basically sits there by itself. So that's actually possible as well. So I'm not so sure you need to mix metal silos with plastic liners if the metal silos, particularly like the Australian design, are designed for the purpose of already being sealed. What you actually need in a properly sealed metal silo, you need a pressure relief valve, because through the solar radiation, it builds up such pressure that it can literally bust open the seams on some of these metal silos. And so that's how the Australians came up with the pressure relief valves that allow those sealed silos to breathe and basically be very tight in terms of air. So.
Okay, thank you. That concludes our 30 minutes for the keynote space. So please join me in thanking Dirk for such a nice overview of the technology intervention area.